Good day, I'm Dr. T. Welcome to my office. And today I want to take a look at our Earth and how it slowly changes through time. Now, a lot of the changes I'm going to be talking about take place rather slowly, and so on human timescales, things seem fixed, but there are definitely changes that happen, even if they're very slow, and there are also definitely changes that happen that are rapid enough that we as humans will definitely start noticing things. So I want to take a look at some of those. Okay, let's talk further reading, both of which are going to be YouTube channels. Once again, I'm going to suggest Myron Cook's YouTube channel, but I also want to suggest Minute Earth's YouTube channel. They do a lot of Earth systems in a nice, short, animated style. Quite informative. I do enjoy their work. Let's start out and let's look at the innards of our planet. This is the classic cutaway image, and we can just kind of work our way from the outside into the inside. So on the outside of our planet, obviously you get the atmosphere and the hydrosphere, that kind of stuff on the outside, you know, the oceans and whatnot. But let's get into the rocks. On the outside of our rocks is going to be the crust, and this is the part that we live on. This is basically all that we've ever experienced directly. Generally speaking, we can kind of subdivide the crust into continental crust and into oceanic crust. Continental crust is going to be both higher and deeper, so it's thicker in both directions. Basically, all the land squishes down, and then the mountains get piled up on top of it, that kind of thing. Whereas oceanic crust tends to be much thinner, both further down, so it's got a bunch of ocean on top of it, but also it doesn't sink into the mantle as far. Now going below the crust, we have the mantle. This is going to be a thick region. It's definitely a fluid, but it is going to be a fluid that is incredibly thick, one that if it was up on the crust and we were just experiencing it day to day, we would probably just call it a solid. But it does flow, and we're going to see convection currents in the mantle becoming incredibly important for us. I should also point out, when it comes to terminology, the crust and the upper part of the mantle together are known as the lithosphere. So basically the rock sphere, where these are where we're normally thinking about when we're talking about geology and rocks, etc. We've never drilled a hole all the way through the crust. The crust is, while on a global scale relatively thin, as far as something you want to drill a hole through, it's a lot, and the mantle is much, much more as far as depth. Okay, moving in from the mantle, we've got the core, and the core gets subdivided into the inner core and the outer core. The inner core is going to be a solid, whereas the outer core is going to be liquid. I should say the inner core is believed to be solid. We're starting to get towards the limits of our understanding, but we're fairly confident it is a solid, where the outer core is a liquid. Radioactive decay within the core. You've got a bunch of radioactive elements floating around. As they decay, they generate heat, and that's going to create a lot of heat from the core that's then going to transfer up from the core through the mantle via convection currents out into the crust, and then we're going to see that in forms of geothermal vents and volcanoes and the like. But before we get there, I actually want to make one quick caveat that the standard picture of the Earth that you normally see isn't quite right, because we assume nice, clean spheres. One, the Earth is an oblique spheroid, although you wouldn't really notice it unless you measure carefully. Because the Earth is spinning, it kind of bulges out in the middle and a little bit squashed on the top. So it's mostly a sphere, but not quite sphere-sphere. There are the large low shear velocity provinces, basically kind of liquidy bubbles within the mantle around the core. So the core is kind of bumpy. There are two of them, one roughly located underneath Africa, the other roughly located underneath the Pacific Ocean. The exact understanding of what these things are is still an object of question and kind of why they are, but we definitely know that it's not just a nice clean sphere. The innards of the Earth are a little bit lumpy and bumpy. Now, you may very rightfully start asking, how do we know what the innards of the Earth look like? Because you've just said we've never even drilled through the crust, let alone all the way down to the center. So yeah, legit question. Generally speaking, there are two answers. If you have an earthquake happen, which happens from time to time, you've got the S waves and the P waves getting sent out, and they don't just stop a few hundred miles away. Especially with the big earthquakes, you're going to have S and P waves traveling through the mantle, through the crust, potentially even through the core. The P waves will go through the core, the S waves will not. And they're going to be felt all over the planet. Now, they're going to be much weaker once you get farther away, but if you've got a seismograph, they will be able to detect it. And over the last 100 years, we have covered the planet in seismographs. So whenever we get an earthquake, we start seeing the waves from the earthquake interacting throughout the rest of the planet. Now, as a wave, if you remember back from my video on waves, as a wave changes medium, then it is going to be changed itself. It'll be redirected and modified. And as such, if we understand what's going on with the waves, then we can start using that to backfigure what must be going on inside the planet. I should also point out, for particularly large earthquakes, the seismic waves will travel through the Earth and actually bounce off and will start bouncing around within the Earth, giving us quite a bit of information about what's going on within the Earth. This is a classic approach for understanding what's going on below the surface. Not only can you do this on a global scale, you can do so on a local scale. It is not uncommon to set up seismic sensors around an area of interest and then set off an explosive charge or drop a really heavy weight to create a big thud, and you listen to the waves as they propagate through the Earth. Now, you're not going to go all throughout the Earth if you're just dropping a big heavy metal block, but you are going to get seismic waves around you, which gives you an idea of what's going on, at least within your local soil. Now, there is another approach that's a little bit more recent for understanding what's going on within our globe, and that is using satellites. Recently, this century, we have started putting up satellites that track their orbit very precisely. And by doing so, they can measure the small deviations in Earth's gravitational field. And well, why would there be minor deviations in Earth's gravitational field? That's because the Earth is not a uniform ball. We quite often think of things in terms of gravity as, calculating from their center of mass, but not all the matter is at the center of the mass, and where the matter is distributed does have an impact on the gravitational field, especially if you're measuring with very high precision, and you can see very small minor fluctuations, which highly calibrated satellites are able to do so. Now, as I mentioned, we have convection currents going on within the mantle, and this is going to have some fairly serious consequences, or at least fairly important consequences. I don't know if I want to say the word serious, although, everything can become serious. Because you have these convection currents, you get forces on the crust. You've got your solid crust, but it's going to be pushed from below in different directions, as well as heat's going to be coming up in different locations. You're going to get kind of hot spots. You've got mantle sinking in other locations, so you're going to kind of be pulling and pushing the crust. This causes the crust to break up into a multitude of what we call tectonic plates, basically large chunks that can kind of start floating around because they're being pushed around by the convection currents within the mantle. Now, if we've got our plates, we can observe them doing a couple of different things as they interact. We could imagine a plate. If two plates are moving, they could be moving towards each other. In which case, we're going to see some subduction going on. We would call this a convergent plate boundary, and one will go under the other. Now, if it's an oceanic plate going against a continental plate, oceanic plates are thinner, generally lower density, so they are going to go underneath the continental plate. This is great for making a bunch of volcanoes as you're slowly, very slowly, once again, not on the scale of human lifespans, you're very slowly melting the oceanic plate as it's diving deeper into the mantle, getting hotter and becoming more fluid. And this is one of the reasons why we have, say, the Ring of Fire, where the Pacific plate is crashing into basically all the other plates. Not all of the other plates, but you get the idea. You've got a lot of subduction zones going around the Pacific, as the Atlantic is actually growing and pushing the North American and Eurasian plates closer to the Pacific plate. Now, if you've got an oceanic plate and a continental plate, you get nice subductions. If you've got two continental plates, remember those are thicker and they start to bunch up. You got a bunch of land. It doesn't usually one go under the other. One will kind of start going under the other, but you got all this land on top and that starts piling up and you start building mountains in this case. So as the two plates are crashing into each other, the mountains are going to get squished together and you're going to start, it's got to go somewhere, so it's going to go up. Now, mountains are actually limited in height on Earth because if they get too high, they actually start getting too heavy and they start sinking into the mantle, and the bottom part of that part of the crust is going to start melting. If you try and make a mountain too high, you're actually going to start sinking in, and it kind of has this feedback loop. The Himalayas are a classic example where one plate is crashing into another plate, in this case the Indian plate crashing into the Eurasian plate, and as such the mountains are being built up in this location and they are currently growing. By the way, I should point out, when it comes to the plates, one of the reasons we're able to know which one is crashing into which one, we observe the rocks and see what they're doing, but we can actually put on GPS trackers. These plates are only moving at a centimeter a year or something on that order. Some are moving much faster than others. But this does mean that we can track the locations, and with the high-grade survey level GPSs, we can track their motion. We can also use that to predict things like earthquakes, which I will get to here in a couple of topics. Now, you got your plates converging together. You might be building up mountains. You might have this nice little subduction zone, which likes to get some volcanoes. But alternatively, your plates might not be going together. They might be going apart. In this case, you have a divergent plate boundary. As the plates are going apart, you're going to have a little bit of an issue. You now have a gap taking place, and you're going to have to fill the gap. So a couple of things can happen here. If you've got land, so you've got a continent, and you're actually splitting the continent apart. Land on one side is going to go one way, land on the other side is going to go the other way, and you're going to create the opposite of a mountain. You're going to create a valley, what we call a rift valley. You're creating a rift, and it's going to be opening up. Eventually, water is going to flood in, and you're going to get yourself an ocean. We can see this process currently taking place in Africa in the Great Rift Valley. Now, once you have your ocean formed, if you keep pulling apart, quite often you can start building up a ridge, and we see this in the Atlantic. So as your continents are pulling apart, there's no more crust in that spot, or the crust is thinning enough that you're going to start getting magma oozing up and filling in that area. So you're going to get a chain of volcanoes, and we can see this with the Mid-Atlantic Ridge. As the plates are pulling apart, you replace the crust, or you build more crust in the form of a ridge. Sometimes this might even poke above the water, in which case you get something like Iceland, a volcanic island. It should be noted that the motion of plates are not fixed. They can change over time. The plates are being moved by the motion of convection currents in the mantle, and as those convection currents change, so can the motion of plates be changed. The Great Lakes region of the United States has some rather unique geology, and this is in part believed to be the result of a forming rift valley that stopped forming. And thus the valley was created and then got filled in, thereby leading towards the unique geology of the Great Lakes and the particularly high abundance of native copper. Additionally, with divergent boundaries, they can become rift valleys, but before so, especially if they're going to be stopping their motion partway through, you can actually get mountain ranges. We can get what is known as fault block mountains. In this case, as the crust is stretching apart and thinning, parts of the crust can sink down or tilt, and this will result in a series of mountains and valleys. We can see something like this in Nevada. Now, you can go together, you can go apart, or you can go past each other. So this is called a transform boundary. Probably the most famous of this is going to be in California. So think San Andreas Fault. So you've got two plates, they're going past each other. And in this case, we're not going to get a subduction or a rift valley, but as they're moving past each other, they're not exactly lubricated. You're not going to have this nice, smooth transition. Rocks are kind of on the sticky side. Depending on your geology, depends on how sticky this is going to be, but your energy is going to get built up into effectively like a spring tension within the rocks, and then eventually, as the plates are moving, something's going to give, and they slip. So you get this start, stop, kind of like moving a rug where you're jerking it. These jerks are earthquakes. So this is where we get earthquakes from. Depending on the geology and depending on how fast the plates are moving, you may get lots of little earthquakes. That's probably the best case scenario. Alternatively, it may take a long time to build up, and then you get a massive earthquake. And the danger of this one is it may take longer than kind of human lifespan. So you forget that you can have earthquakes in this area because the last one is not within even remotely living memory. The earthquake in Zhejiang province, I am certainly mispronouncing this, in the late 2000s was definitely a case here. We didn't realize this region of, in this case, China, had earthquakes because they were very infrequent, but the ones we had were very big, which is, shall we say, a bit of a problem. But we are able to monitor. This is about the same time we're starting to get good GPS tracking on continents, and we're starting to see which ones are moving. And you kind of run the math back like, okay, well, if it's moving and it's having every, say, 1,000 years, it's going to move a lot when it does move. And that means big earthquake. Now, when it comes to earthquakes, the damage quite often to humans, etc., if you're out in the middle of a field, unless it's a really big earthquake, it's probably not going to do too awful much damage to you. However, if you are something that's built into the ground, like a building, that shaking is usually not something buildings are optimized to handle. As such, they tend to fall over, and if the earthquake probably won't get you, but the building landing on you is a very different story. We got multiple different waves coming out of the earthquake. We've got the P waves, the primary waves. These are a compression, so they're going back and forth wave. You've got the S wave. Those are kind of going in an up and down approach. And then you've got the surface waves. So these are the really dangerous ones because they're definitely doing an up and down. You've actually got a couple different versions of these, but they're a lot more dramatic when they're on the surface, right above your epicenter, basically the part that slipped. And as such, these are where a lot of the damage comes from. Now, you can engineer buildings to survive at least medium-sized earthquakes. And so places like California, which know they get a fairly decent number of earthquakes, or over in Japan, they will be optimized to be a somewhat protective building. But if you're a region of the world where you haven't had an earthquake in 10,000 years, you probably are not building a building designed such they can survive an earthquake, and then all of a sudden you get a great big giant earthquake. Now, there's one other interesting danger for particularly large earthquakes, and that is what's known as liquefaction. Liquefaction happens as the earth is shaking, if you've got soils, so not rock, but soils, especially if you got some water going on in there, so your water table's a little bit on the high side. As you're jiggling, the soil is going to rearrange and is going to temporarily become a fluid. Buildings aren't built to be boats, and so all of a sudden, if it's floating in a sand-water mixture, or this kind of liquefied soil, it's probably not going to float particularly well because buildings aren't built to be boats most of the time. And consequently, more damage occurs. Things can get submerged in. You can actually get what are called sand blows, gases and liquid and other things underneath the soil as they get rearranged actually squirt up, and you get these like globs of sand on the surface. Now, when we want to measure the magnitude of the earthquake, so how bad it is, we don't actually use the Richter scale much anymore. The Richter scale was the original one, and this is based on Earth's motion within the area. It's been updated to a local magnitude scale. There's actually multiple different approaches. So we've got several different scales. Generally ones like the Richter scale are referred to as local magnitude scales. And these are looking at the Earth's motion at the location of the earthquake, so kind of like right above it. These are logarithmic scales. So a magnitude 1 is really small. A magnitude 2 is a little bit bigger, still pretty minor. But the difference between, say, a magnitude 8 and a magnitude 9 is absolutely profound. It's 10 times as large. So 10 times a big thing is a really big thing. 10 times a little thing is a slightly less little thing. Now, let's talk volcanoes. As I mentioned earlier, if you've got areas of subduction, you've got a lot of nice magma building up, and, well, it's going to go somewhere. Once it's well under the surface, it's magma. But as it's starting to get above the surface, and once it's cleared the surface, we now call it lava. The chemistry is, of course, going to vary depending on your local geology, what is going on in that area. And the chemistry of that lava is then going to impact the type of volcano you get. Now, you can have subduction zones, but you can also have hotspots. So let's start off, let's look a little bit at Hawaii. So Hawaii is above a hotspot. Basically, it's in the Pacific plate. You don't have a plate border around it, but because of the convection currents within the mantle, you get a bit of a hotspot underneath that. And so now magma goes up to the surface because it's a little bit on the warmer side there. And as magma goes up to the surface, you get yourself a nice volcano. The local geology there, though, creates a lava that is very fluid. It very much flows. It doesn't have a lot of trapped gas, so it doesn't want to explode. Now, it will still go, splurt quite nicely, don't get me wrong, but it definitely wants to oozle and flow outwards. This then builds what we call a shield volcano. And Hawaii, or the Hawaiian Islands, each one are effectively shield volcanoes. This is one where it goes slow enough that if you need to run away from the lava, you should be able to run away from the lava unless you're really close to it as it's going up. As such, an active volcano of this type is not that dangerous. It's not dangerous, but it's a lot safer than the other ones I'm going to describe. Shield volcanoes are generally going to be wide and relatively flat because the lava just kind of oozes out fairly evenly. Now, let's look at the volcano that you normally think of as a volcano, and this is going to be the stratovolcano, or the composite volcano. In this case, you've got a little bit more going on with your lava. You've got a bit more gases trapped in here, and so when this thing goes up, it can vary. Its eruptions can kind of change up a bit, but these eruptions can be a lot more violent, and they can send up a lot of lava, but they also send up a lot of ash, and they can be much more explosive. In a worst case scenario, you can get a pyroclastic flow. This is a superheated cloud of gas, dust, rock racing down the mountainside at extreme speeds. So this is one of those things, whatever it meets is destroyed. This is what destroyed Pompeii. Also, Herculaneum was destroyed in the same eruption. We always forget about poor Herculaneum, but they were also destroyed. Pompeii gets the press because it kind of was preserved very nicely. Herculaneum, just a bit less press. Famous composite volcanoes, you're going to think something like Mount Fuji, Mount St. Helens, obviously Mount Etna. Classic famous example. Okay, the last type is going to be the cinder cone or the splatter cone. In this case, we're sending up not really so much lava, but more of ash and small chunks of rock that are being kicked up. So ash, cinders are a little bit larger than ash. And they're going to kind of pile up. You'll notice the the shape of these. The shield volcano are very, very flat. The stratovolcano tends to be kind of on the tall side. The cinder volcano is a little bit in the middle, and usually has a pronounced crater on the inside, where that's a little bit less pronounced for the composite and shield volcanoes. Okay, last thing I want to discuss on volcanoes before I move into the wonderful world of erosion is that of atolls. Atolls are islands, kind of. They're a rather unique little island. So they start out life as a volcanic island. So you get yourself a volcano, it pops up above the surface, and it does the whole volcano thing. Now, a coral reef starts forming around it. Coral can only survive in shallow water, so it can't start growing in the middle of nowhere. It needs relatively shallow waters so that the algae living within the coral can get plenty of light and be happy and make food and keep the coral happy. But, as all things do, the volcano comes to end. It starts sinking, either due to changing in sea level, the sea floor subsiding, and of course, erosion could definitely take a place in this one. The volcano ends up subsiding well below the surface of the water, leaving this kind of lagoon on the inside, or basically you've got ocean outside and you got this donut-shaped island around it, and we call that an atoll. We see this a lot in the South Pacific. Let's go from building mountains up to tearing them down. Let's talk weathering and erosion. Weathering is going to be breaking rocks into smaller and smaller pieces, whereas erosion is taking those pieces and moving them elsewhere. So let's start with weathering. It generally comes in two flavors, physical versus chemical. Basically, this is the old physical versus chemical change kind of thing. So the simplest form is things being beaten together. This is called abrasion. So if you've got a river, you've got some rocks into it, or if you've got some wind and it's carrying some sand, as the sand or the rocks beat together with other things, then they're just going to physically chip off pieces of them. This is, by the way, why river rocks are so smooth, because all the high points get beaten away as the rocks rumble around in the riverbed. Now, another form of physical weathering is kind of the dominant one, and this is known as wedging. And there are several ways to wedge open the rock, but the idea is you've got a little crack, and then you make it a big crack by wedging it open. The most obvious and kind of the classic way is with ice. So you've got a rock, it's got a crack, the water gets in, it freezes, water expands, now the crack is bigger, it melts, more water comes in, it freezes, the water expands, the crack gets even bigger. This is one of the major reasons why potholes happen. So you got this freeze-thaw cycle. But it doesn't have to be water doing this. You can also get a similar effect with salt. So seawater goes on the rocks, seeps in the cracks, the water evaporates, leaves salt crystals, those tend to expand, wedging open the cracks, repeat, repeat, repeat. Or we could have things like roots. So you can have trees and herbaceous plants sending in their parts. And hey, as the roots grow, they break open the cracks and make them larger and larger. So living systems can be involved with this. Additionally, though, living systems can engage in chemical weathering. So if you have a mineral that is particularly susceptible to, say, acid, like the carbonate, so things like limestone and marble. If you have acid, which could be something from rain, rain is typically a little bit acidic due to carbon dioxide in the atmosphere, more so if you are burning sulfur-containing minerals like coal, and therefore generating sulfuric acid in the air, and you get your acid rain. But this will work just fine with just carbon dioxide. You don't need the sulfuric acid going on. The rain is acidic as it meets carbonate-bearing minerals. It can help dissolve them, turning those into CO2, liberating the calcium if it's a calcium carbonate mineral, and thereby starting to dissolve the minerals. This is how we get karst features. Think caves, sinkholes, and other gaps within your limestone. If you're building in an area with lots of limestone, this is a particularly important feature to keep in mind when it comes to building stuff, because you might be building on a big hole due to the gaps in karst geology. That said, these make some epic caves. If you ever have a chance to, say, check out Mammoth Cave up in Kentucky, absolutely amazing. There's a reason it's a World Heritage Site. If you want to hit up in Tennessee, there's Ruby Falls over in the Chattanooga area. Nowhere near as big, but definitely has a really cool underground waterfall. You should totally check that out. So you got a couple of caves, always fun. So if you can hang out in the cave, you can check it out. And also, you know, if the water is dissolving the limestone, it's going into the water. You've got those minerals don't just go away, they go into the water. And so they can be deposited elsewhere. And this is how we get stalactites and stalagmites and a bunch of other features within the caves by having the water dissolve the minerals one place and redeposit them someplace else. But dissolving the minerals isn't your only option. Water can also react with minerals that are anhydrous and make them hydrates. So if you have, say, calcium sulfate, anhydrous, you can react with it to form the hydrated form, which is gypsum. This is going to be generally slightly larger, so it's going to kind of swell up. This gets put under the chemical weathering because you are forming the hydrate. Remember, the distinction between chemical change and physical change can be fuzzy on a good day. As I mentioned, life can get involved with this. So I mentioned acid. Hey, a lot of living systems, especially some of your fungus, think lichens. Which is Freddy Fungus took a lichen to Alice algae. So they're an algae living in a fungus. They will sometimes excrete an acid to slowly dissolve the surface that they're on, giving them valuable minerals. This is quite often part of reclamation. So if you've got a volcanic island, there is no soil. So the fungus are going to move over. You're going to start getting your lichens on the island, as well as weathering is going to start happening. And this is where you get soil from. So if you want soil, you need the biological material, but you got to start with the inorganic components of it. And this is going to be from weathering, and thus building up a soil layer that then later larger and larger plants can move into your, say, volcanic island or your area which originally didn't have soil. Now, you can also do other chemical reactions. Oxidation is a classic example. Some minerals are going to be relatively reduced. You can oxidize them, typically with oxygen. Sulfides are a particularly common one here, where you've got sulfur 2-, and that can be oxidized to turn into sulfate. Sulfate's much more soluble. Sulfide does not generally dissolve in water, whereas sulfates very much do so. But there ends up being an interesting side effect to this. Sulfates, as they are forming, they react with water. So the sulfide reacts with oxygen and water to form sulfate, but it actually forms sulfuric acid. So the water becomes extremely acidic. This can become a major issue if you've got a lot of this going on, and we see this with old mines. So back in the past, and still in the present, but these are usually decommissioned mines, we dug into the ground looking for various valuable minerals to then process. Classic would be iron sulfide, so a form of iron ore that will then process into iron. Well, you still have trace amounts of the sulfides around, and by trace, I mean you actually have quite a bit. It's only economically viable to get the really pure minerals out. The more dilute ones, they got a bunch of other minerals you don't want. That's not generally economically viable, so those are left alone. And well, once you're abandoned the mine, you stop pumping out the water, and the groundwater quite often floods back in. Depends on what your water table is. And now you've got water, you've got a big hole, so you now get some oxygen. The oxygen dissolved in the water as well as coming in through any gaps. And that then reacts with the sulfides in the ground, forming sulfuric acid, which is very acidic. Also, you get the dissolved iron and other minerals, so you can get a lot of heavy metals in there as well. Iron's not usually considered a heavy metal, but you could have other elements in there that would be deleterious to life. And so now you get this water that's flowing through here that is extremely acidic, very, very low pH, and potentially very rich in metals, and not necessarily in a good way. And this acid mine drainage can be a massive problem, as it can completely destroy an ecosystem and have major pollution. This is something that up in Appalachia, the Ohio, Pennsylvania areas are very much dealing with due to their long history of mining and the environmental impact thereof. We're breaking down our rocks and minerals into smaller components, which are much more susceptible to being transported somewhere else. That transportation to somewhere else is erosion. And you've got about 3 major ways of doing this. One, they can simply fall down, good old gravity. You can have a landslide, the boulder could fall off the mountain, that kind of thing. They're not going to go very far, but they are definitely going to move. And you can imagine if a mountain is slowly being broken into smaller and smaller pieces, if it's a tall, spiry mountain, they're going to kind of fall down to the bottom pretty easily. Now, a little bit more distance or a little bit more aggressive, we can do wind. As wind comes by, they can pick up small granules and brush them along. We saw this with the Dust Bowl. As the winds would pick up, if it was particularly dry, the soil wasn't well attached. Agricultural practices at the time had been very aggressive and were not leaving cover crops or windbreaks. As such, the wind could keep going straight, pick up a lot of the soil, and blow it away. And we saw a large part of Oklahoma get blown away. This was a major ecological problem. Changing farming practices can definitely help address this. Now, as the wind is blowing, it's got particles, they can be flying by and they can be hitting other things and they can do abrasion, and you can start getting weathering and erosion patterns very distinctive of wind. The other major player is going to be water, and water is interesting because it can be liquid water or it can be ice, and both will flow. Ice is a solid, but it will flow if you squish it hard enough. So let's take a quick look at glaciers. So glaciers, you get a bunch of snow, it packs in, you get a bunch of ice, and the weight of the ice shoves it down the mountain. And so the glacier can flow. And as it's flowing, this massive thing of ice, it's going to be scouring the ground. It's going to pick up any loose debris. Not to mention, it's got boulders in there, and it's a solid. It's going to push against the rocks. So it's not only going to be transporting material, it's also going to be weathering it. It's going to scrape out a valley. Glacier scrape valleys are typically U-shaped valleys. Keep in mind, these things are big and wide and they're pushing pretty hard. Now, of course, as you are transporting this material, it doesn't go away, it's going to go somewhere. So if the glacier starts to recede, the material that was in the glacier just kind of drops off. It's no longer being contained with it, because generally the glacier recedes not by moving back up the mountain, but by melting faster than it can flow down the mountain. And so you'll get piles of material from glaciers, thus aggregating what you had scraped from one place and aggregating it into another location. Now, when it comes to water, liquid water does a pretty good job as well. It moves a lot faster, but a little bit less aggressive. You can do erosion with ocean waves. There's definitely parts of the world where the ocean lapping up against the side of the land is slowly eroding it, taking the material into the ocean, and cliffs, say, collapse. We see that a lot in Great Britain for certain parts of the island. But also flowing rivers can etch into the ground. Now, the pattern of the erosion is going to depend both on the rate of the flow of water, but also the geology around it. If you've got fairly rigid rock, something that the water has about as much difficulty going side to side as down, or maybe it's easier to just flat out go down because of gravity, you're going to get deep V-shaped valleys. Think something like the Grand Canyon or other, nice canyons. However, if the water can more easily go side to side, it quite often will go side to side. So if instead of on, say, rock, you're on much more of a soil-based, a nice plain, where erosion is a little bit easier for the water, then quite often it'll erode off on the sides. You're going to get a wider river, but you're going to get this interesting feature where it starts bending around. Due to Bernoulli's principle, as you're going around a bend in your river, the water on the outside of the bend typically goes faster than the water on the inside of the bend. This makes it more aggressive at eroding the material on the bank of the river. So the river is going to erode towards the bend. Now, on the inside of the bend, as the water is going around, it's going to slow down a bit. It kind of bunches up a bit. As the water slows down, it's going to have less turbulence and less ability to keep the material it's eroding in place, and it's going to start depositing it. So now you're depositing on the inside of the bend and eroding from the outside of the bend, and you're going to be exacerbating it. We've created a positive feedback loop. So a small wiggle in the river is going to get bigger and bigger and bigger, and eventually it's actually going to loop back in on itself, and that large bend is going to get cut off, and the river channel is going to go more or less straight again until, once again, another bend starts building up. This remnant of the original river channel is known as an oxbow lake. And so now you have yourself a lake, and eventually it may very well fill in, and you kind of forget where the river is. By the way, this does mean that rivers on plains like the Mississippi are not necessarily a great spot for setting up borders, because the river will move. Now, the rivers will eventually generally end up in the sea. Occasionally they could end up in, say, a lake that doesn't go to the ocean, but we'll assume they're going to the ocean because most of the really big rivers do. And once they go out to the ocean or to the lake, to be honest, this does apply to the lake, then they've got a bunch of sediment. Now, the river flowing, the action and the motion of the river churning up the sediment keeps the sediment in suspension, because a lot of what the river is eroding is in suspension. And if you slow down the turbulence, it will settle. So as it goes out into the ocean or the lake, it slows down and it settles, and you start building up a delta. This is this fan-shaped area of land. It's going to be separated out based on size. So the bigger chunks are going to fall first, and the further out into the lake or river you go, generally you're going to get smaller and smaller particles, so you're going to get finer and finer sediment. And this is quite often a wonderful place to grow crops, because the type of soil that gets eroded from upstream quite often is very nice, high quality for growing crops, because crops like kind of your medium, small size particles, generally speaking. But of course, that's assuming there's a lot of erosion coming down from upstream. Depending on your geology, you may not get that much erosion coming from upstream, and the tidal action of the ocean potentially could create a fair amount of erosion. Not to mention the river does, once again, tend to move back and forth a bit. And so when you're right at the end, You could get a delta where the river kind of fans out with lots of little streams dropping off sediment, but if the erosion from the ocean and other sources happens to be more than the amount the river's depositing, you can get the opposite of a delta. You can get, instead of a fan shape on the outside, you're going to get a V shape at the end of the river where the river widens out. We call this an estuary. Whether or not you get an estuary or a delta is very much dependent on both the body of water you're going into and how much sediment you're bringing down from upstream. So with that said, have a wonderful day, and I will see you in future videos.